Alright, Assalamualaikum and a very good day to all. So for today, we would like to continue the chapter 2, alright? So we have gone through a little bit in our previous class, right? So today, I hope we can finish this part 1 of Fourier series. Alright, so a little bit recap, or let's look again what is a Fourier series, yeah? So we in this Fourier series, yeah, we're gonna see there are two types of domain. Okay, there is a time domain signal and also frequency domain spectrum. Okay, and both, okay, and this frequency domain spectrum can be expressed into a signal expression or complex exponential. So this is what that we will cover today. Perhaps we have been covered some of it in our previous class, right? Okay, so now let's go to Fourier series. So what is Fourier series actually? So Fourier series is to represent infinite sum of periodic signal, okay, for example sines, cosines or exponential, in a form of simple signal. Okay, so we are using this Fourier series, okay, to form or to represent periodic signal. Okay, so we know that periodic signal can be sine, cosine, all right, so in a form of another simplest way of signal. Okay, and usually it is a sinusoidal signal. Okay, so so these are the types of periodic signal. Okay, we have sine, okay, we have a square signal, we have a triangle, we have a sawtooth. All right, so this, okay, for example, okay, we have equation like this, okay, where vt, okay, we assume that this is a vt, the y-axis is a vt. Okay, so v is equals to plus minus n, which is the numbers here, of t naught. So what is t naught? T naught is the fundamental period. Okay, so how do we decide the fundamental period? Okay, we're going to start from the first point until one whole complete signal. So this is the T naught, yeah, the first, usually the first signal. Okay, for example, for square, which is start from here and gonna finish until here. All right, so yeah, until here. Okay, so this is the one, T naught, yeah, for the square. And for the triangle, since that it begins from here, so you're going to end here. So this is the T naught, and same goes to sawtooth. Yeah. Okay, where can we apply this Fourier series? Okay, these are where the fields that we can apply this Fourier series. Yeah, and then how can we represent this Fourier series? So Fourier series, okay, or usually we make it as Fs. Yeah. Okay, so Fourier series can be represented into two types of forms. Yeah, the first one is the trigonometric form, and the second one is the complex exponential form. All right. So this is the how we want to represent the Fourier series. Yeah. So this is I add on where I didn't explain in the previous class, yeah. So the advantage, a little bit of advantage of Fourier series, yeah. So what are the advantage of Fourier series? So the signal, yeah, generated commonly is a non-sinusoidal. Okay, in the real world, okay, the signals that is generated or that is showed to us, yeah, commonly is a non-sinusoidal waveform, right? Okay, it can be either sawtooth, it can be triangle, it can be in an envelope way, right? So but periodic, okay, although it is not non-sinusoidal shape, but it is a periodic, means that it has a repetition, yeah. So which are difficult to analyze. So since that it is a non-sinusoidal, all right, so however it is periodic, but then it's quite difficult for us to analyze, yeah. So therefore here comes the Fourier series where, okay, we use the Fourier series to represent, yeah, any form of periodic signals, okay, into a sinusoidal form, okay, into a sinusoidal form, so that it can make us easier to analyze that particular of signal. Okay, for example, this kind of we have this kind of equation, okay, where this is the omega naught, this is the first period, yeah, and then this is the second term, this is the initial term, and this is the following terms, and this is the next term, and this is the next term. Okay, so now let's look this signal. And for the first term, yeah, for the first term, if we try to plot this particular signal, okay, it's gonna looks like sinusoidal shape. All right, this is a sinusoidal shape. However, if we add the first term with the second term, if we add the first term and the second term, it kind of looks like this, right? Okay, there's going to be some distortion at the peak and at the lower peak here, at the upper peak and at the lower peak here. All right, it's not it's no longer what we called it, a nicely form of sine wave, right? So there's going to be a distortion, right, at some parts. Okay, so how about if we add the third term together? So if the first term plus with the second term plus with the third term, you can see that the distortion now become much more obvious, okay? And then at the peak, yeah, at the peak, either lower peak or upper peak, the distortion are gonna be much more clearer, and the slope are gonna be much more steeper. Okay, this is the slope is slanting like this, okay, much more I mean, we can see the gradient clearly here. All right, and then when we add the first term and the second term, it's going to look much more towards this straight line, right? And when we add the first term, second term, and the third term, it becomes much more steeper, which is becoming much clearer into a straight line. How about if we add the fourth term? Okay, we can see here that if we add all the terms together, it's nearer to a square signal, right? Okay, it's nearer to a square signal. All right, so here we can say any periodic signal can be represented by a series of sinusoidal signal. Okay, you can see here the square wave actually, all right, the square wave actually, okay, can be represented by series. So this is the series, yeah, by series of sinusoidal signal. Okay, if we add the first term, second term, third term, and fourth term. So this is where, or this is how, or this is the advantages of a Fourier series, right? So now this is the signal spectrum. Okay, so now let's look into the signal spectrum. So periodic signal in time domain can be represented, okay, periodic signal can be represented in time domain, okay, it can be represented in time domain, and also can be represented by its amplitude and phase spectrum in frequency domain. So the periodic signal actually can be formed or can be represented into time domain or frequency domain. If it is represented in a frequency domain, it can be either amplitude spectrum or phase spectrum. Okay, so for example here, this is the amplitude modulation, okay, where you are going to learn this much deeper in PCOM later on, yeah, in your third year. You're going to take this courses, yeah. So for example, we have an information signal here, okay, it is represented as FM here. So in order for the FM to be transmitted, okay, to pass through to this modulator, it needs another carrier signal, where this carrier signal, the amplitude is going to be much more higher compared to the information signal. All right, so if these two signal here, the information signal and the carrier signal, if we add together, okay, after it's passing through the modulator, okay, after it's passing through to the modulator, so what are the modulator doing? The modulator is actually adding these two signal, the information signal and the carrier signal together, Okay, so therefore it will gonna be modulate, yeah, the signal, and it can be represented in a time domain. This is how it gonna looks like if we represent both of this signal after it's passing through this modulator. It will gonna look like this. This is in the form of time domain. All right, where you can see here it is envelope of modulated signal. It looks like a module envelope here, yeah, where it has a minimum amplitude and maximum amplitude. So this is when you represent the output, yeah, the output signal as a time domain, right? So how if you can we can also represent the output signal is as in a frequency domain. So if it is represented is in a frequency domain, it's gonna look like this, yeah. So this is the carrier signal. Okay, I will not explain much more in this because you're gonna learn this in your third year, but this is how the difference between the time domains look, okay, and the frequency domain. So in the frequency domain, you can see here that the signal going to be divided into two, which is we can have a upper sideband at this part, and this part is known as lower sideband. Okay, and this frequency domain, as I mentioned just now, okay, to represent this the periodic signal, okay, to represent the periodic signal, we need to use the signal spectrum, yeah, the signal spectrum. Again, we need to use the signal spectrum, and to have the signal spectrum, this signal spectrum, okay, can be divided into two types of spectrum, which is the amplitude spectrum or the phase spectrum. Okay, so this frequency domain, okay, so this frequency domain, it can be represented as this. We're gonna have two, yeah, double sideband. Okay, gonna known as double sideband here. Okay, this is the conventional. Okay, this is the double sideband, and it also can be represented as single sideband. Okay, either upper or lower. Okay, either upper or lower here. All right, so this is what we're going to look today. Okay, we're going to learn today where in some cases, okay, you're going to represent that particular signal as a double sideband. In some cases, you're going to represent that particular signals into a single sideband. All right, okay. So now I think this is same as what we in your previous slides, yeah. So the signal expression. So the signal expression. Okay, for example, this is the time varying voltage signal. Okay, so this the one that is A naught here is known as amplitude. Okay, and then whatever inside that particular brackets, the omega here is the angular frequency, okay, where omega naught is equals to 2 pi f, all right, and the theta here is known as the phase. Okay, inside this bracket, it can be divided into two. One is the angular frequency and another one is the phase form, yeah. And this can also be represented as cos sine. All right, so we know if we know that signal actually, for example, the sine, yeah, this is sine, right? If we delay, okay, if we delay this signal at pi over 2, we can have sine, sorry, cos signal. So you can always transform the cos signal into sine signal by minus, yeah. For example, if cos you want to change into sine, you have to plus. Cos into sine, you have to plus pi over 2. If sine you want to change into cos, you have to minus pi over 2. All right, so for example here, you have a sine here. Okay, you can represent it into omega naught as 2 pi f naught, and you can change from sine into cos by minus pi over 2. So in this case, if you want to change into cos, okay, for example, you have a naught cos omega naught t, and you want to change into sine form, so therefore it can be sine omega naught t plus, yeah, pi over 2. All right, so you can always what change the form, yeah. Okay, so now let's look into the time domain signal. So okay, so this is what I've explained just now. Okay, you can see here cos and sine. It's always delay or advance as pi over 2. So if you want to change from sine to cos, you have to minus pi over 2. If you want to represent cos into sines, you have to plus pi over 2. All right. So let's look into the frequency domain, which is we also known as a spectrum. Okay, frequency domain signal, also known as a spectrum. So each sinusoidal signal has a frequency f. Okay, usually frequency is represented as hertz or angular frequency as omega. So it can be represented into two, either hertz or either omega. All right. All right. Okay. So if this is a frequency form here, if it is in and then the amplitude is represent as A and the phase is represent as theta. Okay, for example, you have this equation. Okay, you have this equation. So this equation is known as a polar form or trigonometric function. Okay, it's known as a trigonometric function or polar form. Just now I already mentioned, right, that the spectrum can be represented into trigonometric function or exponential function, right? So first of all, let's go into the trigonometric function. So this is how it is represented into a trigonometric function, all right, where you're gonna have for example, a1 cos 2 pi fy t plus uh, theta y plus, okay, plus a2, okay, cos 2 pi f2 minus 2 pi f2 t minus theta 2. Okay, so now let's look into details this equation, yeah. So the first one, okay, the first one is known as the amplitude. Okay, the first one is known as amplitude, and whatever inside the bracket, the first term, okay, where if there is a t inside here, so this is gonna known as omega. Okay, and this is gonna be the phase form. All right. Okay, now let's identify how many component that we have inside this equation. So this is the first component, and this is going to be the second component. So therefore you're going to have two signals, yeah. All right, so the first signal, the first component, let's look into the first component. The first component, the amplitude is a1. Okay, so this is the first component. The amplitude is known as omega 1. Wait, yeah, so this is omega 1 and this is omega 2. All right, so this omega 1 gonna be on this component, yeah. This is going to be the first component, this is going to be the second component. Okay, and same goes to the phase, right? And then since that this is going to be the amplitude spectrum. Okay, so this is the amplitude spectrum. So to know the magnitude of the amplitude, you need to look at the in front here, yeah. So the first component, the amplitude is a1. The second component, the amplitude is a2. All right, so and then same goes for the phase spectrum. The first component, the phase is, since that it is positive, so it's gonna facing upward, while for the second component, the omega is minus, yeah, minus, so therefore it's gonna face downward here. All right, so another things that you need to take notes for the trigonometric function is, for the trigonometric function, okay, wait, all right, so good. Okay, for the trigonometric function is trigonometric function. This trigonometric function always, okay, will have a single-sided spectrum. Okay, what I mean by single-sided spectrum, it gonna be only one side of the spectrum. For example, in this case, the side of the spectrum is only on this part, on this particular side. You will not have at the negative part here. Same goes to the face. You will not have on the negative part here. Okay, so trigonometric function always, yeah, will represent a single-sided spectrum. Okay, so please remember this. Okay, now let's look into the example. Okay, now let's look into the example. I think we have discussed the example in the class. All right, so plot the amplitude and phase spectrum for the signal below. So these are the example of the signal. Okay, where A cos omega naught t minus B cos 2 omega naught t plus C sine 3 omega naught t. So in this case, we're going to see here, we have the first term, second term, and third term. Okay, and then if we can see inside here, we have, okay, we have cos. All right, the first term is in the cos form. Okay, cos, and then the second term is same as the first. I mean, it's still the cos. However, it is a minus in front here. Okay, and the third term is sine. Okay, so they provide you the hint. Okay, they provide you the hint. So to represent the signal, okay, the best way is always make the first term, yeah, the first term plus second term plus third term. As I mentioned, it will be only in a single-sided, right? So make sure that all the terms are gonna be in a positive side, So therefore, you have to change this. You have to change this into another representation. I mean, use the hint, okay, to solve it. So you need to rewrite this equation. How? This is how it gonna looks like, where negative cos theta is equals to cos theta plus pi. Okay, you plus pi. So this term, okay, inside that particular bracket, so this is actually the brackets, right? Inside this bracket, you need to plus pi. You need to plus pi. So therefore, in front here, instead of negative, gonna be positive. All right, so now the first term is the first term is perfect. You're gonna have positive term here, this is cos, so okay. However, the third term, it is not in a cos form. You're gonna see inside this equation there is a cos and sine, combination of cos and sine. So to make or to represent this particular signal, you have to change all the term to be uniform. I mean, if it is sine, you change everything into sine. If it is cos, you can change everything into cos. So since that we have already two cos here, so the easiest, I mean, the shortest way is the third term, you convert it into cos. So how? You use into this hint, yeah? So sine theta, okay, is equal to cos theta minus pi over 2. All right, cos theta minus pi over 2. All right, so minus pi over 2. So now you're gonna have a uniform term. Everything gonna be cos. All right, and now we can represent the signal. Okay, we can represent the signal. So if you can plot the signal, okay, the first term, it has amplitude A, so A it is. The second term, it has amplitude B, so B it is. The third term, it has amplitude C, so therefore C it is. All right, so the first term is omega naught. Okay, so this is the omega axis here. So the second term is 2 omega naught, and the third term is 3 omega naught. All right. So in this case, since that the value of A, B, and C is not given, so we just wrote it as A, B, and C. So how high the amplitude is doesn't matter as long as you wrote the value of this amplitude. Yeah. So we know that the value of A, B, and C is different. Yeah. So therefore that's why the height is different here. You can also represent as A is much more higher than B, or C is the highest compared to others. So that's no problem. Yeah, since that the amplitude is not given, I mean the real value is not given, so the height of each here we just assume. But the most important thing is you write the value of this amplitude at this particular signal. All right. So for the phase, okay, so since that the first term there's no phase, so therefore it is 0. Okay, the second term the phase is positive pi, so therefore it's kind of facing upward. And the second term, since that it is negative pi over 2, so therefore it's facing downward. All right, so now there's another condition. All right, so there's another condition. For example, if they're given to you this kind of equation, all right, this kind of equation, and they ask you to plot. Okay, so how? So the so how to plot this kind of equation is, we can convert this equation. I mean, we can convert this type of form into an. Okay, the amplitude is going to be an cos omega n t plus theta n. So to use this particular term, I mean to use this particular formula, okay, to use this particular formula, the most important things that you need to, I mean, you need to highlight, or um, you need to take note is, wait a minute, yeah, I change the ink color. Okay, the most important things that you need to highlight is, make sure that the value of omega here, the first and the second, is same. Okay, so now in this case, both are gonna have omega n, right? So therefore, you can convert this term into this particular term. So therefore, it's gonna be an cos omega n t plus theta. So how did you want to decide now the value of an and theta n? How to decide this? So to decide the value of an, gonna be the amplitude of this cos. An is the amplitude of this particular cos square plus the amplitude of sine, the amplitude for sine square, and then square root together. All right, equals to, and then this is how you want to decide the value of the amplitude for these terms. Yeah, and then how to decide the value of theta. So the value of theta can be decided by tangent inverse minus bn, which is the amplitude of sine, divide by an. All right. So actually, this bn and an is known as the function coefficient. Okay, so for bn, this is the function coefficient for sine, since that this is sine. So this is the function coefficient for sine, and for an, going to be the function coefficient of cosine. Yeah. So therefore, after that, you can straight away, I mean, you can straight away plot this spectrum. Okay, so this is the amplitude, okay, and this is the or magnitude, okay, amplitude or magnitude, and this is going to be the phase spectrum. Okay, all right, I hope up until here you clear. Yeah. Okay, now let's look another example. Okay, sketch the magnitude. Okay, now the question asks you to sketch the magnitude and the phase spectrum of a signal which is given in the form of trigonometric Fourier series. So it's already mentioned, given to you now is a trigonometric Fourier series. Yeah. So let's look into detail how many terms that we have here. We have the first term, second term, third term, and fourth term. All right, and then let's identify I mean the uniformity of this equation. So we can see here there's a combination of sine and cos, right? There's a combination of sine and cos where the value of omega is the same. All right, where the value of omega is the same. So therefore, I think we can, however, combine this to be as what I mentioned like this, right? Since that the value of omega is the same. All right, and then so that is the first work that you have to done, okay, before you sketch the signal. And the second things that you have to, you have to pay attention for this in this equation is there's a minus here. Okay, so we know that the trigonometric Fourier series form gonna the signal will be only in one side, so therefore there shouldn't be a combination of plus and minus, right? So we need to do something here. Okay, we need to do something here in order to convert this, to make this into plus. All right, so now let's rewrite this equation. Okay, so for the first part, since that we know that the omega naught here, the sine and for the cos is the same, right? So now let's apply what we have learned in the previous slide just now. So if we rewrite the order to be the cos at first, so it's going to be 2 cos omega naught t plus sine omega naught t. So from here, we can, so this should be as an, right? It should be as an cos, an cos omega naught t plus theta, right? Theta n, right? So this is cos, yeah? So we need to identify the value of cos, the value of amplitude and the value of phase. All right, so to find the value of an, so the amplitude here says that it is 2. So 2 squared plus 1 squared, so therefore it's going to be square root of 5. And the value of phase is going to be tangent inverse minus bn, so the value of bn is 1, and then divided by 2, so therefore the value of your phase is going to be minus 26.56 degree. Okay, so therefore this value will going to be square root of 5 cos omega naught t plus, minus 26.56 56 56 56. Okay, I think I did wrote here. Yeah, okay. All right, so the value of an gonna be here, the value of theta n gonna be here. And then we have to do something, right, for the behind here, to make sure that this is going to be positive term. So cos you want to change into cos, in order to make it as positive, what we're going to do is you plus pi. All right, so for example, you have a cos here. If you plus another pi, okay, if you so it is negative, right? It is negative. So if you plus another pi, it will be positive, right? It's gonna be positive. Okay, so okay, negative here. If you plus another pi, it's gonna be positive, right? Yeah, the amplitude up here and down here is gonna be same. All right. So to make it into positive here, you have to plus pi. All right, plus pi. So therefore, from here, I think you can straight away plot the signal. So this is the amplitude spectrum. Okay, amplitude or magnitude, yeah, amplitude on the magnitude spectrum. So the first term, which is at 0, it's gonna be 1. Okay, since it's only provide you the value of amplitude. And then the second term, which is omega naught. So omega naught, it is actually square root of 5, so it's equals to 2.24. And then the second term, which is the third term, yeah, you're going to be 2 omega naught. So this is 2 omega naught, where the amplitude is 2. All right, so and then this is for the magnitude spectrum, yeah. Whereas for the phase spectrum, okay, for the phase spectrum, the first term doesn't given to you the value of 0. The value of phase, so therefore it's gonna be 0. The second term, the value of omega, the value of phase is gonna be minus, so therefore it's gonna facing downward. So we can convert this into in a pi form. All right, so you can since that this is in a pi form, so you can do either one. Yeah, either you want to put it as degree or pi, but then usually we represent it in a pi form, right? So you have to convert this into pi form. All right. So it kind of looks this way, right? So this is the answer. Yeah. So now let's look into the phasor representation. So the phasor sinusoidal signal can be shown as x-axis or y-axis projection by an anti-clockwise. Okay, for the positive phase value. So if you have a positive phase value, okay, for example, you have the value of pi. So since that it is positive pi, so you're gonna start from anti-clockwise from your x-axis, you're going to go into anti-clockwise positive value. But if you have negative pi, for example, negative phase value, right? So what you're going to do is going to face downward here. All right, so if it is negative, it's going to be in clockwise. If it is positive, it's going to be anti-clockwise. Okay, that is going to be the rotational of the phasor. All right. Okay, so now let's look into the another representation of signal spectrum, okay, frequency spectrum, where we can represent it as the Fourier series here can be represented into a complex exponential representation. Just now we have discussed about trigo. Okay, so now let's look into the complex exponential. So right. So for the complex exponential, okay, for the complex exponential, it's used to analyze a signal. Okay, we use the complex exponential to analyze a signal, same as trigonometric function. So in general, we represent it as this. Yeah, I mean this is the trigonometric function. Okay. However, this function, if we can convert this function by using Euler's theorem, where then it can be represented as this, which known as complex exponential representation. Okay, where it can be represented as ej omega t plus theta naught equals to cos omega t plus theta naught plus j sine omega t plus theta naught. All right, so whatever inside the bracket is going to be cos, going to be bracket inside the for cos plus j, okay, they're going to be imaginary here, j sine, and then whatever inside the bracket in front here, going to be inside here. Okay, so this, how to convert this is by using Euler's theorem. Okay, I think you for this equation, yeah, please look back with the previous handout that I given to you. I think you need to, you need to correct this, yeah, because in my previous slide I put it as j theta, right? Cos theta plus j sine theta, right? However, it's supposed to be omega t plus theta naught to make it as uniform as the first equation here. So please change here, yeah? It's supposed to be j omega t plus theta naught here. Okay, so this equation we can form, okay, in a sine form, where sine omega t plus theta naught is equals to e j omega t plus theta naught minus e whatever inside the bracket inside here. For here, where the only difference is you need to have an minus here. Wait, yeah, to have a minus here. Okay, so this is in a sine form. In a cos form, okay, in a cos form also gonna be minus here, but the only difference here is negative and positive. Okay, negative and positive. So you can always convert it into in a sine or in a cos. Okay, if it's sine, the down part gonna be 2j. Okay, if it's a cos, it's gonna be 2. Okay, so now let's look into okay, so this is the trigonometric, okay, trigonometric form, and this is the complex exponential form, yeah, complex exponential form. Okay, All right. So okay. All right. So now let's look into the exponential form. If it's just now I mentioned, if in a trigonometric function, okay, your spectrum will gonna be in a trigonometric form. Your function, your spectrum will gonna be in a single side spectrum. Gonna be only on a single side, right? However, if you represent it into exponential form, it will be in a double-sided spectrum. Okay, what I mean by double-sided, you're gonna have either positive, negative, positive, negative. All right. Why there is a positive and negative? Because now you can see here, because of this, your omega now, the first term is positive, which is this one. The second term is negative omega, right? So therefore, it's going to be negative form. So if the question asks you to represent that particular, to sketch the signal as double-sided, so you need to have this exponential equation. All right. So this is going to be the amplitude, okay, as usual. This is going to be the amplitude. And then for the phase, this is going to be the phase value lah. Alright, this is going to be the phase value. So for the negative, the phase value, although it's positive here, but don't forget there is a negative. So negative, positive, so therefore it's going to be negative here. Alright. Okay, so now let's look into uh, in a phasor form. How about the phasor form? So phasor form just now, okay, phasor representation, if it is in a trigo, okay, if it is in a trigonometric function, okay, it will be, it gonna look like this, right? It gonna look like this, where if it is a positive, it gonna be anti-clockwise, yeah, anti-clockwise. If it is negative, it gonna be clockwise, right? Okay, so how about for exponential? So for exponential, okay, you're gonna have both. Okay, you're gonna have on the side here and on the side here. Okay, you can always have both, yeah, because you're gonna have the positive of phase and the negative of phase, yeah. So this is the difference between the trigonometric function and the exponential function, yeah. So in a trigonometric function, your phasor representation will be only one side, either positive or negative, based on the equation here. If in an exponential representation, it must have two. It's going to be positive and it's going to be negative. Yeah. So for the positive, you're going to be start from here, from this axis, anti-clockwise. For negative, we're going to be from this axis and clockwise. Yeah. So, in a summary, for example, time domain versus exponential form. Yeah, for the I mean, this is the repetition from the beginning. Yeah, for the trigonometric function. Okay, so this is the trigo. You're gonna have a single sign. Okay, for both amplitude and for the phase. However, for the exponential, okay, for the exponential, you're gonna have a double sign. Okay, double sign for exponential Fourier series. So please bear this in mind. Okay, so now let's look into example. So this is example 1. For the continuous time periodic signal, it's given to you this equation. So the question asks you to represent the signal in the form of complex exponential Fourier series. So since that it mentioned to you complex exponential Fourier series, by now you should you should bear in mind, or you can have the clue that your signal must be in a double side. Okay, since because of it mentioned complex exponential, right? So it must be in a double side. So how to do that? And then sketch the double-sided frequency spectrum. Okay, so first of all, this from this equation, uh, what you have to do is you have to convert, because this is in a trigonometric function, right? Trigonometric function. So you have to convert this into exponential. Okay, using what? Using Euler's theorem. Okay, you have to represent, to convert from the trigonometric function into exponential function, you need to apply the Euler's theorem. So first of all, you need to know, you need to identify if there is any frequency sharing inside this equation. So now let's see inside this equation. This is the first term. There's no frequency provided. This is the second term. The value of the frequency is 2 pi over 3, right? And then this is the third term where the value of the frequency is 5 pi over 3. So it is not similar, right? It is not similar. So therefore, there is no frequency sharing inside this inside this equation, because omega naught is not the same with omega 1, right? And then next we have to rewrite the equation. So how to rewrite this equation? How to make it easier? All right. So first of all, we need to convert one of them. Either you convert cos or you convert sine using the Euler's theorem, right? So if you want to convert cos into sine, if we go back into the Euler's theorem just now, I showed to you, if we go back to the Euler's theorem just now, from cos, if you want to change into sine, there will be imaginary 2j down part here. So it's going to be quite difficult. So you can do this, but I'm not recommended. Yeah, because there is 2j down here. So this is going to be troublesome, or going to be much complex, because there is a 2j. So you have to consider 2j for the whole of your calculation later on. So instead of convert the cos into sine, so the easiest way is for you to convert sine into cos, because cos, there's no 2j. It's only divide into 2, right? So okay, so how to convert that? So to convert sine into cos, wait, yeah, pen. All right, to convert sine into cos, as I mentioned just now, you still remember at the beginning of the lecture, I mentioned sine into cos, they're going to be minus pi over 2. All right, minus pi over 2. So change this into minus whatever inside this bracket, minus pi over 2. Okay, pi over 2. And then from here, you're going to have cos, cos. Okay, so now it's easier. You have both the same, yeah? So the first term, you doesn't have to do it much, yeah? Nothing calculation needed, because it's only provide the amplitude too. Okay, so now cos, how you want to change into Euler's is whatever inside the bracket, e exponential, j whatever inside the bracket, plus e minus j whatever inside this particular bracket, and divide by 2. Okay, so if just now you change cos into sine, okay, so you have to consider 2j down the down part here, and this should be minus, right? And this cos is going to be plus pi over 2, right? And then for this term, okay, for this term, if you want to convert into exponential, so it's going to be e j whatever inside the bracket is going to be in front here, plus e minus j whatever inside the bracket is going to be behind here. All right, so from here you can simply solve it. So it's going to be 2. All right, so half is going to be 0.5, and then it can be e j 2 pi over 3t plus e minus j 2 pi over 3t, plus this is going to be 2. So 2 ej whatever inside that particular bracket, yeah, whatever inside this particular bracket. And then from here you can straight away draw or sketch the amplitude spectrum. So the first term, okay, the first term, okay, so the first term is given as 2. I think I forgot here. There should be 2 here, yeah? There should be 2 here. Okay, I forgot to do for the 0 part here. Okay, so it is 2. Okay, 2, and then at the at omega equals to 2 pi over 3, the amplitude is 0 0.5. Okay, so this is the positive. And then at negative 2 pi over 3, the amplitude is still the same, 0 0.5. And then for the third term, at the positive 5 pi over 3, yeah, 5 pi over 3, the amplitude is 2. And then the minus 5 pi over 3, the amplitude is 2. Okay, so now you have double-sided, yeah. Okay, so next is the phase spectrum. So the phase spectrum at 0, since that there's no value of phase here, so therefore 0 it is. Okay, and then for the second term, since that there's no phase included inside here, so it is 0 it is, yeah. And then for the third term, since that it's gonna be for the 5 pi over 3 at this omega, yeah, at this omega, the value of the phase is minus pi over 2, positive minus, so it's going to be minus pi over 2 downward, and then negative, so it's going to be positive. So at minus 5 pi over 3, it's going to be positive, so therefore it's going to be facing upward, pi over 2. All right, so this is how we want to apply, or we want to solve from the trigonometric functions into a exponential, okay, into exponential by using the Euler's theorem. Okay. All right, so these are the list of complex form that you can use later on. Okay, later on in chapter 2, where ej theta is equals to cos theta plus j sin theta, ej pi over 2 is equals to j. All right, ej 3 pi over 2 is going to be e minus j pi over 2, and it is equals to minus j. All right, and then as the following, and also you need to know this graph as well. For example, okay, for example, j pi and then j minus pi. Okay, so this is actually from this graph. Okay, you can see here. Okay, you can see here, it starts from here, yeah. If your j is positive, for example, your j is pi over 2, so pi over 2 is 90 degrees, yeah. So it's going to be, this is pi over 2, right? Pi over 2. So your value will going to be j. The value, I is j, yeah? I is j. Okay, your value is going to be positive j. Alright. However, if it is going to 3 pi over 2, so 3 pi over 2, so it's going to be positive. Since that it is positive, right? So it is anti-clockwise. So start from here. So it's going to end at this part, right? So it's going to be negative I or negative j. In this graph, they are using the imaginary part as I. However, in our class, we're going to use as j. So it's going to be negative j. All right. So it's going to be negative j. And same goes for this term, for this equation, negative j pi over 3, negative j pi over 2, sorry. So since that it is negative, so it's going to be clockwise, right? You're going to use different color. So it's going to be clockwise, right? So it's going to be down here, facing down here. So it will be minus j, right? So it's going to be minus j. All right, and then for j pi, so it is positive. I mean, it is positive, so it's going to be anti-clockwise. So you will get minus 1, right? So for j negative, e exponential minus j pi, so it is negative, so it is anti-clockwise, right? Sorry, it's going to be, since that it is negative, so it's going to be clockwise. So it's going to be here. So the results of j pi and negative j pi, so it's going to be minus 1, sorry. Okay, minus 1. So you have to, I mean, instead of your remembering this equation, sorry, up until here, yeah? Instead of your remembering this equation, okay, you can just, I mean, remember this circle that I provide here. But you just have to change here I into j, 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 and I into j. And same goes this as well. Ej pi, so ej pi, since it is positive, ej pi is going to be, ej pi is going to be minus 1, right? These were going to be minus 1. So therefore, if you plus 1, so it becomes 0, right? Okay, so instead of you remembering this, please I mean familiar with this graph. Okay, so therefore in your exam you can draw this by yourself. Yeah, you don't have to memorize, but then if you understand, you can draw this uh, you can draw this by yourself, right? So I think that's all. Thank you so much. If you have any questions, if you have any, if you want to ask anything, please freely to email, or you can DM me as well. All right. So thank you so much, and uh, see you guys in next lecture. All right. Thank you.